Hi guys. So I was hoping that we would be able to start light today and how electrons are what exhibit certain type of properties that have to deal with light. And unfortunately in third bell we didn't get a chance to start talking about light. We just got done talking about all of our periodic trends, so I would like to spend this video at least talking about half of the slides that have to deal with light, so then that way we can finish them up tomorrow, and then that way we can review on Thursday for your test on Friday, okay? I know it feels like we're going pretty fast, but I want to make sure that we get through this stuff so that way we can have time to do more fun things. So if you would look at the slides that I attached for you on this post on the blog, I'm just going to start off with slide number 1. So in the early 1900s, there were certain elements that emitted a different color of visible light. And a lot of scientists were curious why some compounds or some metals or some elements would emit one color of light, but they wouldn't emit another color of light. So while scientists kind of analyzed all of these different maybe hypotheses that they were thinking, they found out that an element's chemical behavior is really related to the way that the electrons are arranged around the nucleus, which is why you've been writing these electron configurations. So we think of light as being what we can see. So if you look on slide 2, I wrote visible light is a type of electromagnetic radiation. Now, visible light, what we can see, is just one tiny part of this overall spectrum of electromagnetic radiation. So I want you to understand that what we see in light is a type of radiation, and specifically we will call it electromagnetic radiation. Now there are other types of electromagnetic radiation, and we're going to see those other types on this next slide. So visible light is a type of electromagnetic radiation, and it's a form of energy that exhibits some type of wave-like behavior. When I say wave-like behavior, what I mean is that light literally is going to act like a wave. It has movements up and down, up and down. So it literally looks like a wave. I skipped this on the first slide, I'm so sorry. On the first slide I said something about wave-particle duality. What that means is scientists are baffled that light could act not only like a wave, but it could also act like a particle. So what we see in terms of light, we think that it will act like a wave. But other scientists believe that light acts because of little tiny streams of particles that move in one direction. So some scientists believe that light will act like a wave, and then other scientists believe that light just consists of these tiny little particles that move in a straight line or in a certain line. So that's all that wave-particle duality means. And when we get into physics and we start, like if you were to take AP Physics, once you get into physics, you'll start learning more about how light, we've seen at least experiments that show light acting like a wave and also light acting like particles. So there is evidence for both. So that's why we call it wave-particle duality, because we really don't know, since it acts like both. Maybe it is both. Don't know. Okay, so electromagnetic radiation is on a spectrum. So we would call it the electromagnetic spectrum. And there are several categories of different types of radiation that's on this spectrum. So if you would look at slide number 3, I gave you a little graph here. So this right here is your electromagnetic spectrum. So if you look at the left side of that spectrum, I have this little bracket thing and it says radio. So radio waves are a type of electromagnetic radiation. And actually, if you also read this little graph that's underneath here where you see radio, it categorizes these radio waves by wavelength. So as you move from left to right, the wavelength should become shorter. So as we're moving from left to right, the wavelength becomes shorter on this spectrum. So wavelengths for radio waves have really, really long wavelengths. So radio waves have really long wavelengths, and that's that first type that I can see here on my spectrum of the electromagnetic radiation. The next one that I see are microwaves. So microwaves is a category of electromagnetic radiation. The next one is infrared rays. Infrared rays, this is what, so gross. This is what snakes can use to try to find food. They supposedly can see in infrared. So in infrared, we think of mostly heat. It has to deal with like thermal energy. And we can't see in infrared. We can only see in visible. But snakes supposedly can see in infrared, which is so gross. As we move next to the next category, it's visible light. And you know that visible light is that spectrum of colors. We would say it's Roy G. Biv. And we say Roy G. Biv because that symbolizes, or at least that gives us, all of the colors. So we have red, orange, yellow, green, blue, indigo, and violet. So I would just say Roy G. Biv. And that would be all of our colors. Now, if we think about these colors, I want you to understand in visible light that red has the shortest wavelength. So red has the shortest wavelength, and violet has the longest wavelength. Has the longest wavelength, okay? We're going to talk a little more about that in just a second. If we look at the next category on the spectrum, it's ultraviolet light or ultraviolet radiation. And you can think of this just like the sun can emit all of these UV rays. You can get sunburned or suntanned based on those UV rays. That's a type of radiation. The next one is X-rays. We're all pretty familiar with those. You go to the hospital because you maybe have broken your arm and they have to give you an X-ray. So that's a type of radiation. The last one that I have listed on the spectrum are gamma rays. Those are very, very dangerous and powerful rays. They have the shortest wavelengths on this spectrum. They also have the most energy. They are very, very energetic. They have lots of power to them. So gamma rays can actually penetrate through our skin and get into our DNA and mess up our DNA or mess up our cells or mutate our cells. So gamma radiation is really dangerous to us. But these are just some of those categories that are on this electromagnetic spectrum. And I want you also to write down for me while you're taking these notes that we said that the radio waves have the longer wavelength, and we said that gamma rays have the shortest wavelengths. But gamma rays have a lot of energy because they're much more powerful than radio waves are. So will you write for me that when wavelength, so let's write when wavelength gets smaller, when wavelength gets smaller, we have more energy. So the type of radiation will have more energy. So when the wavelength gets smaller, then we end up having more energy, okay? They are inversely related, meaning as wavelength goes down, energy goes up, okay? So I'd like you to write that on that slide for me, or in your notes. The next slide has to do with certain parts of a wave. So let's label some of these parts on a wave, okay? So on the next slide, I gave you an example of a wave. So if you wanted to look at that with all the parts already labeled. And, oh, guys, I completely messed up my wave. It looks too hideous. Okay, so we can see here on that slide it says that we want to label the characteristic called the wavelength. Okay, so here's my wave. Now, a wavelength, it says, is the shortest distance between equivalent points on a continuous wave. So if I look at my wave here, I have a top point here, which the top point on a wave is called the crest. So let's just go ahead and label that. the high point on a wave is called the crest, and the low point on a wave we call the trough. So we have the high point is the crest, and the low point is called the trough. And again, those things are already labeled for you on that next slide, okay? So high point on the wave is called the crest, low point is called the trough. But we want to label what the wavelength would be. And the wavelength is where I can start having a repeating type of unit, or a repeating wave. So once I get from this crest, I move down, go to the trough, and then I move back up and I've reached another crest. So because I've reached this second crest, it's like I'm going to start repeating that wave all over again. So once I'm at this crest, I move down, I go back up, I'm at another crest. And then I'm going to repeat that all over again. Move down to the trough, go back up to a crest, and then it's going to repeat again. Crest to trough, back to crest. So from crest to crest here, those are two equal points. That is what we would call your wavelength. So from crest to crest could be a wavelength. Or if I had a trough down here and then a trough down here, which I do, from that trough to that trough, that would also be considered a wavelength. Now, wavelength, we give a certain symbol, and you can see that next to where it says wavelength that's labeled on your slide. We give it a little symbol that kind of looks like an upside down Y, looks like this, and that's